We add up the reciprocals of the squares on and on forever. It is addition a third grader can do, and there is not a circle in sight. 1 plus 1 over 4 plus 1 over 9. Every denominator is a perfect square. But push this addition all the way to the end, and out comes this answer. Add up 1 over n squared for every n, and you get pi squared over 6, roughly 1.6449. Pi is a circle's circumference divided by its diameter. A number you can only get by measuring a circle is sitting in the answer to a sum that has no circle at all. So today's goal fits in one line. Smuggle a circle into a problem that has none. The smuggling route is trigonometry. Sine and cosine are points on a circle, and pi is already baked into the radian. Its name is the Basel problem. Pietro Mengele asked the question in 1650, and the answer arrived 84 years later. In 1689, Jacob Bernoulli of Basel got only as far as showing the sum is less than 2, and then asked for help. The one who finally cracked it was a man in his 20s from that same city, Leonhard Euler. The year was 1734. Today we skip Euler's route and travel with 6 high school tools instead. And we work on a genuinely finite polynomial, not on infinity. Before the proof, let's size up what we are dealing with. We add infinitely many terms, so why doesn't it blow up to infinity? 1 over n squared says very little when you see it as just a fraction. Think of it as the area of a square sheet of paper whose side is 1 over n. The 100 sheet has side 0.01, so its area is only 0.0001. The pieces shrink frighteningly fast. Here is Jacob Bernoulli's move. When n is at least 2, 1 over n squared is smaller than the difference of these two fractions. The equality in the middle is confirmed the moment you put the fractions over a common denominator, and the inequality on the left is nothing but the fact that a bigger denominator makes a smaller fraction. Now let's add up the right-hand side from the second term all the way to the last. Neighboring terms pair off and vanish. Every interior term is wiped out and only the two ends survive. It collapses the way a telescope folds shut, so we call it a telescoping sum. So the partial sum is always less than 2. However long we keep adding, it never crosses that threshold. It only grows, yet it is bounded above, so it has to converge. The question is what that value is, and that is exactly where Bernoulli stopped. Stack 10 terms and you get 1.5498. Stack 100 and you get 1.6350. It keeps reaching for the ceiling but never quite touches it. Let's look at the numbers. The target is pi squared over 6, which is 1.644934. Put the remaining distance on a log scale, and as n grows it closes in on 1 over n. To get 6 decimal places right, you need 1 million terms, and even then, you are still 1 millionth short. So brute force computation will never crack this. The exact value has to be caught by an argument. Now we head to the place where every proof begins. A single, almost magical inequality. The 1 over x squared trapped in the middle is exactly the ingredient of the sum we are after. Those two unfamiliar symbols are just reciprocals. Flip tangent and you get cotangent. Flip sine and you get cosecant. Draw a circle of radius 1, mark a central angle x, and 3 regions of different area nest inside one another. Inner triangle, then the sector, then the outer triangle. Multiply through by 2 and you get sin x, then tan x. The middle term is x over 2 only because we measured the angle in radians. Pi has already smuggled itself in. All 3 quantities are positive, so taking reciprocals flips every inequality sign. Squaring positive numbers preserves the order. And that is how we land on the magic inequality from the start. Why go all the way to squares? Because what we want is the sum of 1 over n squared. The condition in the parentheses is not decoration. At x equals 3, the bottom slice shoots past 49 and punches straight through the filling. The left slice first breaks near x equals 2.0288. The right one always holds as long as sin x is not 0. So we always pick the angle strictly between 0 and pi over 2. That restriction turns out to be decisive later on. Here is the finished sandwich. The gold curve is trapped between the blue cotangent squared and the red cosecant squared. And there is one thing worth noticing. The gap between the two slices is exactly 1 everywhere. Thanks to this identity, we will never have to work out the sum for the top slice separately. 3 stages lie ahead. We just finished the first. Next comes building a finite series whose value we know. Now for the heart of this video. It is time to compute the value of the bread. The two slices look different, but a single identity ties them together. It is that famous equation divided by sine squared. So we only need one of the two. De Moivre ties cosine and sine together in a product, which makes cotangent the easy one. We pin down the cotangent first, and the cosecant comes free from the identity. There are two things we want. Raise a two-term expression to a power and it unfolds into a sum. The formula that pulls this off for trig functions is de Moivre's. Take the point rotated by x on the circle and raise it to a power, and you are simply repeating that rotation that many times. There is a reason we picked an odd exponent of all things. Apply it first, and if it goes wrong, fix it later. Expand with the binomial theorem and the terms come pouring out. A power of the imaginary unit I rides on every one of them. The real part is awkward since there the exponent on cosine is odd. So we collect the imaginary part only. The signs swing back and forth because I squared is -1. We divide both sides by sine to the power 2m plus 1. Then nothing but the cotangent is left. Sine and cosine vanish wholesale, and only the cotangent survives. That is the payoff for choosing an odd exponent. We shift the viewpoint just a little. We take the whole chunk cotangent squared and call it y. The trig functions are gone, and a familiar polynomial is all that remains. Its degree is exactly m. Euler borrowed the rules of polynomials for an infinite object, but what we hold is a genuinely finite polynomial. Now we hunt for the roots. For the left side to be 0, the angle only has to be an integer multiple of pi. So x is our pi over 2m plus 1. At r equals 0 the cotangent is undefined, so we start from 1. At the top end we take r only up to m because the magic inequality lives between 0 and pi over 2. Had the denominator been even, the last angle would perch right on the boundary. That is one more reason we chose an odd number. Reason 2. Pushing r higher gives no new roots. The two angles are symmetric about pi over 2, so their values match. What is more, cotangent squared only decreases on that interval. Different angles give different values. So we can use Vietta's formulas with a clear conscience. The sum of the roots is minus the next coefficient over the leading coefficient. Summing cotangent squared for r from 1 to m gives m times 2m minus 1, all over 3. Let us check the smallest case by hand. When m is 2, the two values add up to exactly 2. When m is 3, the three roots of the cubic are exactly the cotangent squared values. And the three roots add up to 5. Push m from 1 all the way up to 12, and the two bars always stand at exactly the same height. Every ingredient is on the table now. Now let's put all the pieces together and squeeze the sandwich shut. Into the magic inequality we substitute our pi over 2m plus 1, and add it up over r from 1 to m. The middle is the easy part. Just flip the fraction over. The front factor has nothing to do with r, so it slides out of the sigma, and at last the sum we've been hunting for appears. On the left, it is exactly the value we just got from Vietta's formulas. On the right, the fact that the two slices are always exactly 1 apart really pays off. All that happens is that one gets added m times. We never had to work out the top slice separately at all. And so all three slots of the inequality get filled in. To leave nothing but the middle, we multiply the whole inequality by pi squared divided by the square of 2m plus 1. On both sides all that is left is a fraction built out of m alone, with not a single trig function in it. Factor it and write it again and you can see the ending coming. Both sides are pi squared over 6 times two fractions that sit close to 1. And as a bonus, even the top slice never gets past pi squared over 6. Bernoulli's upper bound just got dramatically tighter. Now let's send m to infinity. Divide top and bottom by m squared, and on both sides you can see exactly why. The two slices wore completely different faces, and out at infinity they meet at pi squared over 6. The value caught in between has nowhere left to go. By the squeeze theorem, there is only one possible answer. What we squeezed was the partial sum, and the definition of an infinite series is precisely the limit of those partial sums. So we got the existence of the limit along with it. The gap thins in inverse proportion to m. To nail down the third decimal place, m has to go past 2600. Here is the squeeze carried out for real. Even pushing m up to 2000, the two slices agree only to the second decimal place. But that doesn't matter at all. We did not compute the value. We proved that the value could not possibly be anything else. Once you have come this far, one question is bound to cross your mind. So what about fourth powers? What do you get when you add up 1 over n to the fourth? We will not need a single new tool. Come to think of it, we pull just one thing out of that polynomial, the sum of the roots, and threw the rest away. Vieta's formulas tell us far more than that. The roots multiplied 2 at a time, 3 at a time, then added up, written in symbols as ek. First, we square the inequality one more time. Everything is positive, so the order stays exactly as it was. Second, this time we need the sum of the squares of the roots. We just take the algebraic identity from middle school and stretch it to many terms. Give it a name and it's the second line of Newton's identities. Even so, all it takes is one middle school algebraic identity. Multiplying in pairs and adding is a completely different number from squaring each one and adding. The sum of cotangent to the fourth also falls out of the coefficients alone. It looks frightening, but when m is 3 it is just 19. The top slice works the same way. Cosecant squared is 1 plus cotangent squared, so all we do is square it. Third, we squeeze it exactly as before. Send m to infinity and only the leading term survives. Now you can see where the 90 comes from. It is just 8 over 45 divided by 16. The same polynomial, the same inequality, the same limit. All that changed is which coefficient we read off. The bonus we had, that even the top slice never rises above the target, is false here. This time the bread wraps the target from above and below. Now that we have come this far, let's give it a name. The Riemann zeta function, and today we pin down zeta of 2 and zeta of 4. Even exponents always give a power of pi times a rational number. Odd exponents are still uncharted territory. One last question. We never drew a single circle, so why was pi in the answer? Pi first opened the door back in section 2. The moment we measured angles in radians, the circle was already inside the formula. But at that point pi was hiding inside the unit, without ever showing its face. Pi showed itself as a number in exactly one line, the line saying that sine theta is 0 exactly when theta is our pi. That pi rode the angle x into the middle of the inequality, and at the very end it came out squared as the answer. So here is the summary. A world with no circle functions that live on a circle, and the door the circle came through. Mathematicians call this proof elementary because it borrows nothing from higher theory. If two friends take your hands from both sides and close in on a single point, you have no choice but to go to that point too. The moment you lay a trigonometric bridge across this sum, pi becomes inevitable. That is why Euler's answer stunned all of Europe. If you enjoyed today's video, please subscribe, hit like, and turn on notifications. See you in the next story.